All right, we are on chapter 34, the nature of light and the principles of ray optics. So let's go to the PowerPoint and share a lot of historical data to begin with. The photograph here shows you the a dewdrop uh, and some of the halos that appear with it. We'll discuss uh, reflection, refraction, um, uh, interference, why you see like water, what appears to be water on a dry road on a hot day, things like that. So let's get right to it. This is Christian Huygens. For um, a long time, the most people thought of the uh, light as particles. Newton described light as particles. He believed that particles were emitted from a light source, and these particles stimulated sense of light upon entering the eye. So this idea of the particle nature of light was pretty prominent. But in 1678, Christian Huygens showed that the wave model of light could also explain reflection and refraction. And Thomas Young uh, showed that under appropriate condition, light waves interfere with one another, just the way waves, audio waves or waves on a puddle interfere with one another. And no one could, uh, there was no way to explain how in the particle nature that how they could cancel one another. And there were other developments, the most important of which was Maxwell. Maxwell showed that the high frequency wave nature of light, light was an electromagnetic wave. Um, and of course, Hertz, as we saw in a previous uh, lecture, that Hertz proved Maxwell's equations by having a transmitter and receiver. Um, Now, later on, we've discovered that there are particles of light called photons. You can think of, it's a dual nature. Light is a dual nature, wave nature of light, and there is a particle nature of light. In his time, Galileo tried to measure the speed of light by having fellows at a distance like 10 kilometers with lanterns and trying to, one opens a lantern and the other one opens the lantern. When he sees it, the first one records when he sees the lantern, and it wasn't very successful because the response time of the people opening and shuttering the lamp was too slow to uh, obtain a reliable speed. Oh, I should have. Oh, there's no picture of Galileo Galilei. That happened the last time with the symphony orchestra. Anyway, I think it's in your book. And then Romer, he in 1675, Romer made observations that led to the first successful speed of light measurements. He noticed that the period of the eclipse of Io, one of the moons of Jupiter, that it changed depending on whether uh, Earth was on the Jupiter side of the sun or whether it was away from the sun. And so um, using that information, he estimated that the lower limit for the speed of light was 2.3 times 10 to the 8 meters per second. Well, we know that it's 3 times 10 to the 8 meters per second. So that was a pretty good, uh, considering the day and the measurement method, that was a pretty good estimate. And it showed that the light had a definite speed, and it gave an estimate of that speed. Now, Fizeau, in 1849, Fizeau had a different method, and it came pretty close. If you can imagine this little wheel turning, and the as the light passes through a gear tooth, if it goes too slow, you'll see the same reflection back at A, and if you increase the speed of the toothed wheel, at some point you'll you won't see anything because it'll be blocked by B. And then if you can just go a little bit beyond, you'll see it at C. So the speed of light would be 2D, twice the distance. You can see the D up here, twice the distance divided by the time it takes. And using, so using the, um, you know, the distance D, the number of teeth in the wheel, the angular speed of the wheel, you could estimate, and Fizeau arrived at a value of 3.1 times 10 to the 8th meters per second. And we know nowadays it is 2.99792458 times 10 to the 8th meters. For all practical purposes, 3.00 times 10 to the 8th meters per second is a usable value. And we'll stick with that. And we'll stop there and go on with the ray approximation and ray optics on the next lecture.